Greetings once again. My name is Mr. D, again with another presentation. Today we'd like to do a frame or a truss analysis using the graphical method. So the frame that you see here is the one that we want to analyze. So when we want to analyze, what we like to do here is number one, to get the magnitude by the reactions, and number two, to analyze each and every member, check its magnitude, and also determine the nature of each and every member. So this is what we have to do. For us to be able to complete this activity, we are going to combine the triangle of forces together with the polygon of forces methods into a single line diagram. So what would be the first step that we have to do? The first step is to redraw the frame. You have to redraw the frame according to a linear scale and make it your space diagram. So when I analyze my frame, it is having a span of 6 meters. So if I can think of a scale, I can use a scale of 10 millimeters representing 1 meter. So let's draw the frame. Let's draw the frame and make it our space diagram. So 6 meters will have to give me 60 millimeters. All right. All right, my reactions, they are here. Right, then we also do have angles, 30 degrees, 30 degrees. So I can use my protractor, or either I can use this pair of set squares. As you know that our set squares for the 30 by 60 degree, we do have a 30 degree here, we do have a 60 degree here. So I can make use of my set squares so that I can quickly do that. All right, this will give me 30 degrees. And then right at the apex there is a 20 kilonewton force, and then if I can drop a line here, I also do have 30 degrees here. I also have 30 degrees here. All right, that's my frame. And then we also have a 10 Newton force acting here. We also have another 10 kilonewton force acting here. All right, so this is 20 kilonewton and this is 10 kilonewton, and we also have a 10 kilonewton here. Okay, and then our reactions, reaction left and reaction right, reaction left and reaction right. Right, now we've done the space diagram. We just need to label it and indicate the scale that we have used. So we also call it a form diagram or either a space diagram. So let's label it. I'll say space diagram. And the scale that we've used said 10 millimeters on paper representing 1 meter. Step number 1 is done. What will be the next thing to do? The next thing for you to do now is to calculate the magnitude by the reactions. To calculate the magnitude by the reaction. As you can see that this is a symmetrically loaded frame, meaning the sum of downward forces should be simply equal to the sum of upward forces. So to get the reactions here, it's not going to be difficult for us. Let's add 10 plus 20 plus 10. This will give us 40 kilonewtons. So if upward forces, or rather if downward forces should be equal to upward forces, it simply means here that we are going to divide, for us to get the reactions, we are simply going to divide 40 by 2 so that we can have our reaction. This is going to give us 20. It simply means that our reaction left is equals to 20 kilonewtons. Our reaction right is equals to 20 kilonewtons again. So this frame, it was just fortunate for us that the frame is in equilibrium, as we can see the way it is loaded here. So we got our reactions. So let's put our reaction left is equals to 20 kilonewton. Our reaction right is also equals to 20 kilonewton. Now we get our reactions. It is now time for us to come to the single line diagram, which is going to combine the triangle of forces together with the polygon of forces into the single line diagram, like I'm saying. But before you do that, you need to apply Bose notation to your frame. So Bose notation, you can simply start from the left hand side, put your A, your B, C, D, underneath it's E. When go inside, we continue the lettering. This is going to be F, G, H. Sometimes we skip I because I can confuse us with the one, so you can go from H, you can go to J, or you can still use I, is still fine. Right, now we want now to come to our first polygon, which is going to be the diagram that is going to help us analyze this frame. So what you do, just underneath the space diagram, just to the right hand side here, you can simply drop a vertical line, because on this line we want to represent the forces that are acting on the frame. Right, there we go. I'm going to decide on a starting point. I'm going to decide on a starting point, of which is fine. I can choose this point, it's fine, which is going to be my A. Right, which is going to be my A, and I know that from A to B it is a 10 kilonewton force. So simply here, what I have to do again here is to make sure that I come up with a vector scale that I'm going to use here. So I'll decide upon a scale that I'm going to use here. If this is 10, we have 20, we have 10. I can use a scale of 2 millimeters. Let me talk about a scale. Let me use 2 millimeters representing 1 kilonewton. That is for my first polygon, or simply the vector diagram. Let me simply say vector diagram. I'm going to use a scale 2 millimeters, 1 kilonewton. So what does it mean? My A to B, that distance will give me 20 millimeters. Then BC is this force, that is going to be 40 millimeters according to my scale here. then CD is going to be 20 millimeters. All right, so my A is here, my B is here, my C is here, my D is here. Then we also need DE. As you can see, DE is our reaction, right? And which is a force that is going up. So from D, I have to measure 40 millimeters, because this is 20 kilonewton. According to my scale, 20 kilonewtons will give me 40 millimeters. So I'll measure 40 millimeters going up. There we go. It means my E is here. So we all have now the external forces or the downward forces, including the reactions, all represented here on this vertical line. Now we need to draw up the members now. For us to do this, we want to show all these members, right? For us to do this, we are going to work with what we call joints or nodes. So I'll just write here, it's a node, that's N-O-D-E, or we can simply say joints. I'll explain what we mean regarding this. So if I can come here, I will say this is a joint, or this is a node. This is a joint or node. Same applies to this joint, same applies here, same applies here, same applies here. So you need to work throughout all those joints when you draw or you complete your vector diagram. And for you to be able to do that, you must choose a joint that is not having more than two unknown forces. What do I mean here? If I come here, for example, I am calling this a point or a joint or a node, and already I do have first force, which is this one. I have AF and I have FE, which is this member. So you realize already that I know the magnitude of my reaction left, which is 20. I only don't know the magnitude of this member and the magnitude of this member. So already I don't have more than two unknown forces, right? Which is a different scenario. If I can try to choose probably a joint like this, I only know this force. This and this and this, they are all unknown forces. So I'm not going to be able to work it out there. So remember earlier on I said we are combining the triangle of forces method together with the polygon of forces method into a single line diagram. Okay, so when I come at this node, because I see three forces acting on this point, this will definitely bring me to the triangle of forces. But on a joint like this one, this will bring me to a polygon of forces. We have 1, 2, 3, 4 forces acting on that node. So if I have to choose, I'll choose this node, and I want to encircle it. Those circles, remember this is a working diagram, and you must show that you have been working on that diagram. It's a working diagram, so show that you've been working on that diagram. At the end, we must be able to trace where did you get the magnitude and the nature of your members. All right, now let me start. So we have the first side of the triangle, which is, remember to move in a clockwise direction when you do this. So the first side is EA. Already we do have that side here, which is EA, one side of the triangle. Then from EA, we now go to AF. All right, so please, we simply use our set squares to transfer this line. We simply mean that we like to transfer this line. This is the line that we want to transfer here. All right, I can simply use these two set squares to do that. Then I bring, because that is AF, already I have A here. If I can draw a line, this line, now you know it is parallel to this line. All right, please, you must be able to practice how to draw lines that run parallel to each other. There we go. Then to complete the triangle, that's our AF. We know that F is along this line, right? But F and E, they have to meet somewhere, which is a horizontal line. We already have E here, so I'm gonna make a horizontal line from E. From E, I must have a horizontal line. Right. There we go. So it means now my F is here. All right. I'm done with that node. I have to go to the next node. Right. Courtesy of this node, I now have the magnitude of AF. I now know the magnitude of AF. What I don't know now is BG or GF. All right. So I can continue in that clockwise direction. I can continue in that clockwise direction. Right. How many sides do I have? Don't forget, this is the direction that you're making. I have this member. Now we call it FA. There is FA one side of the polygon and AB two sides of the polygon. Then we have BG. All right. From B, we need this line. So I'm going to transfer that line from my space diagram. There I am. Right. That's my BG. But what about G and F? Because G and F, they have to meet. GF. All right. It is this line. Already I have F here. Already I do have F here. So it simply means I want to take this line bring it like this, and it must be like this. All right. So what does it mean here? It means that our G is at this point. All right. Right. I continue to move in a clockwise direction here. All right. Here we are done. So I'm putting a circle here to make sure that I'm done with that joint. I move on to the next joint. But before I can start working on that joint, I have to check how many unknown forces do I have. If I'm having more than 2, I have to skip and go on to the next joint. So already I now have GB. I now have GB here. And already I know BC. What I don't know is CH and HG. Right, let's start again. Where is BG? There's B, there's G one side. All right. There's B. Okay, let's start. Okay, it's rather GB, GB, then BC, BC. We now need CH. All right. That's our CH. This is the line that I'm supposed to bring here. So you align, transfer that line. Transfer that line. Okay, that's CH. Let's bring it. Okay, that's our CH. But H and G, we see it's a vertical line. Already we have G here. So if I can erect a vertical line from G, it must bring me straight. It must bring me straight to this point here. So that's your vertical line. All right. So our H is at this point. That's my H here. All right. So I'm done at this joint. I have to move to this joint. 1, 2, 3, 4. Already I do have CH now, isn't it? I know this one. I only need DJ and JD. Let's see if we can work it out here. Okay, let's start with the size that we know. It's HC, that is H, and there is our C. From there, we are saying CD, there is our CD. Then we need DJ, which is this line. That's our DJ, all right? Is this line that I want. That's my DJ. And from D, right, you realize it is just going to come here, go through, right? Go straight. And I know that my J is along this line. I will just have to complete the node. But J and H, they will meet. Already I know my H is here. So if I bring this line, it will take me through straight from H and coming here. You realize that our J and H and F rather are on the same point. Our J and F are on the same point. So we are done with the first polygon. Remember this diagram I said we can also call it the first polygon. It is also called the Maxwell diagram. I remember, I think it is in honor of the guy who produced this method, Maxwell diagram. Okay. Right now, what would be the next step now? The next step now that we have to do now is we would like to check out the magnitude of these members, number one, and also check out the nature of those members. So we just need to complete a table here so that we can tabulate our answers. Let me just complete a table here. Right, in this case, I'm not gonna do all the members, but I will just do probably 5 of them, and then you will be having a hint of what to do next to the remaining members. All right, so our table will say member, its magnitude, member, its magnitude, and its nature. All right, this column will indicate the member. Then this column, we need to determine the magnitude of that particular member, and we will identify the nature. So the nature we are saying, is it a tie, meaning under compressive forces, or is it a strut, the one that is under tensile forces? So the first member that we can identify here is AF. This is a member. All right, so AF, that's our first member that we want to check out. Right, how do you get the magnitude of AF? You simply go to your vector diagram or the first polygon and measure the line AF. So there is my AF. Of which I got 75, 6, 7, 8. This is 78 millimeters. 78 millimeters. So we are saying our AF. Let's do some little calculations. is 78 millimeters, but I've used a scale that says 2 millimeters is equals to 1 kilonewton. Now here I got 78 millimeters. Then how many kilonewtons are we talking about here? So it simply means I have to divide 78 divided by 2 so that I can get the magnitude. 39. All right. I get a 39 here. So we are saying this member is 39 kilonewtons. Right. Now, when it comes to the nature of that member, you're going to work with these two, the space diagram and the vector diagram simultaneously. All right. Okay. And also you just need to make sure that when you talk about AF, you must choose a node that you want to use, right, to identify the nature. So if I choose this node, all right, this member, you call it AF because you have to move in a clockwise direction. If I choose this node to determine the nature, it means this member, you don't call it AF, but you call it FA because you are moving like this. All right. So let me just choose this member for myself at this particular time. I'll call it AF. So I check where is A, where is F. All right. Because I'm using this circle, I'm moving from A going to F, meaning I'm going down. So in this circle, you put an arrow going down in this circle. All right. And then right at the opposite circle, you put an opposite arrow. Obviously, this is according to Newton's third law, which says to each and every action, there is an equally opposite force acting to that force. All right. So this simply means that member, it is a strut. This member, it is a strut. Okay. Probably I can do another member. I've already showed you how to get the magnitude. I just want to emphasize on the nature. The magnitude, you simply come here and measure the lines. I'm sure this is quite easy. FE, we have B, we have BG, all right, and let's just go to GF. Where is GF? There is GF. Let's quickly do that.